I'm going to present a functional Perl that is about finger trees. Right, so the talk is called Finger Trees Explained Anew and Slightly Simplified. So this paper and talk is completely based on a paper written by Ralph Hinze and Ross Paterson in 2006 called Finger Trees, a Simple General Purpose Data Structure. This paper is a beautiful paper, and the data structure that's described in it is absolutely astonishing to look at and try to understand also. Incidentally, finger trees are also the basis of the standard Haskell library data.sequence. I've been trying to understand these finger trees, and in the process of doing so, I wrote this functional Perl. So let's look at these sequence data types. They support a number of operations, and the operations I will talk about in this presentation are mentioned here: head, tail, and cons, last, init, and snock, which are sort of the tools of head, tail, and cons, append, and there's also an indexing operation in Hinze's and Paterson's paper, but I won't talk about that here. So the complexities of these operations, if you look at normal Haskell lists, are constant time for head, tail, and cons because you work on the left-hand side. But if you work on the back, last, init, and snock, then they become linear time. And append is also linear time for normal Haskell lists. Sequences or finger trees, they support head and last in both constant time, but all the other operations in logarithmic time in the size of the sequences. So that is nice. So in many cases, that will be an improvement. But the real killer comes when you look at the amortized complexity of these operations. So the amortized complexity of all of these operations, except for append and indexing, is constant time. So head, tail, cons, last, init, and snock are all constant time amortized complexity, and that's really nice. Well, this is the data type that they give in the paper. This is the data of Hinze and Paterson. So there's a seq data type, which is for sequences. It has a bunch of constructors, and it uses two helper types that I call sum and tuple here. They called something else in the paper, but for the sake of my implementation, my explanation, that works better. And sum is a data type with 4 constructors, and tuple is a data type with 2 constructors. And these are rather similar data types. Now the paper of Hinze and Paterson claims this is a simple data structure, and I must say it's simpler than many of the alternatives that exist out there. But when I try to understand the paper, the natural question is, why do you need these 2 helper data types, and why do they look as they do? Why does sum have 4 constructors and tuple have 2 constructors? And the paper doesn't really explain that. They claim that choosing 1 to 4 elements for sum gives you just enough slack to get the right complexities, but there's no reasoning about that or motivation. So I would like to give that motivation in this paper and in this talk. So my plan is to start with something very, very simple, a very simple implementation of sequences that supports these operations. And as soon as something is not right, we incrementally refine it so that we solve that issue. And hopefully when we've solved all the issues, we get an implementation that looks very similar to the finger trees from Hinze and Paterson. Just going to look at these 6 operators, head, tail, and cons, and last, init, and snock on sequences, and I'm just going to find out how to implement these using their worst case complexities, not the amortized complexities yet. So we want head and last to be constant time, and tail, cons, and init, and snock to be logarithmic time. Okay, so here's our first try. Try number 0, which is just using normal Haskell list. So a sequence is implemented as either nil or cons, and the cons has the usual type. So why doesn't this work? Well, for example, when we have to work at the end of the list, when, for example, the function last, which computes the last element of the list, it has to recurse all over the list. So last is linear time in this size of the list, and that doesn't work. So this is a problem we have to fix in order to get the complexities in the table. And one way to do that is to readily expose the last element of the list in the implementation rather than hiding it somewhere deep in the data structure. So that we're going to have to make a change to seek so that we expose the last element. But of course, we should not forget to expose the first element as well. So it doesn't help just to reverse the list because the head also needs to be constant time. So that's how we make a refinement. And we end up at try number 1. Try number 1 tries to expose the first and the last element readily to the user. And so we end up with a data type that looks like this. A sequence is either empty, or it has one element, or it has more elements, more than one, so at least two. That means we have a first element and a last element that we can represent and expose to the user right away, and the rest of the sequence will be recursively represented using a sequence again. Okay, so this idea of rearranging the representation of the elements so that they become easily accessible to the user is called a finger, and this is the reason why Hinze and Paterson call this data structure a finger tree. Okay, so head and last are now very simple constant functions. They just pattern match out this element or that element for head, or this element and that element for last, so constant time. If we look at the cons function, for example, here's cons, so we add an element to nil or unit, that's easy. But as soon as we add an element to more, the new first element becomes x, but then the y element, the previous first element, has to be pushed inside of q, and this is a recursive function, and we can see that the complexity becomes linear. And that's not what we want. We want the complexity to be logarithmic. So how do we make the complexity of a function like this logarithmic when it's clearly linear in this case? Well, we're going to use another idea that comes from data structure design, and that's we're going to make the recursion faster somehow. So let me explain the idea behind this. Suppose you have a sequence data type that already exists, can be any sequence type, and now consider the following sequence type that I call seq2. It's implemented using this sequence type, but the elements in it are pairs of elements of this sequence data type. So in some sense, one can say that this new sequence type is twice as fast as the old one, because when you do one operation here, it corresponds to two operations there. So that's nice. Now the idea comes, if you use this idea recursively, so if you implement a sequence by using seq2 as its own recursive representation, so at every recursion step, you go twice as fast, and that leads to a logarithmic time behavior. So let's use this idea in order to implement sequences. So this is try number 2. So here's our new sequence data type. Sequence is either nil or it's a unit, or it has at least 2 elements, and recursively represent the elements in between the first and last element using these twice as fast sequences. And now the hope is that our operations become logarithmic. This technique is called implicit recursive slowdown by Chris Okazaki. So head and last are easy to do, but cons has a little problem. So the first 2 cases for cons are just the same, but once we do cons on a list that is represented using more, the first element is easy, but now this element y is to be pushed inside of q, but q wants to have pairs of elements, not just one element. And so we don't have enough elements to add to q. We only have one y, and we need to pair it up with something. And we can easily see this is a bad representation of sequences because, for example, sequences with 3 elements cannot be represented with this sequence data type at all. So how do we fix this? Well, we don't have enough elements to add to q here. So why don't we somehow wait until we have enough elements to add to q? So instead of requiring there must be exactly one y here, maybe if we allow a little bit of slack with how many elements we have there, then we can be sure that once we have to add something to q, we actually have 2 elements in our hand. So we're going to buffer the elements at the start and at the end of the sequence. So what does that look like? Well, let's try number 3. It looks like this. It's a normal sequence data type so far. The only change is that now, instead of having exactly one A at the beginning, at the end, we have some A, and some is a new helper data type that's either 1A or it's 2 A's. Okay, so we allow 1 or 2 elements at the beginning and 1 or 2 elements at the end. So head, for example, is simple. We just pattern match out the first element, and so it's still constant. And from now on, insight is that last, init, and snock are completely symmetrical to head, tail, and cons. And so I'm not going to show you the implementation of last, init, and snock. I'm just going to make sure that the data type design is symmetrical, and each of those 3 functions can be implemented in terms of symmetrical versions of the other 3 functions. So I'm not going to show you these functions, only head, tail, and cons. So let's look at cons. So this is what cons would look like. So consing to a nil or unit is easy. Even consing to a sequence that starts with one y, because now it starts with 2 elements, x and y. So no recursion there. But as soon as we cons an element to a sequence that already starts with 2 elements, now the new sequence starts only with the x, but the y and the z, we pair up and we recursively add to q. And mind you that this is a sequence that goes twice as fast as the original one. So the recursion number of recursive steps that this function does is logarithmic in the size of the sequence in the worst case. So this is a logarithmic complexity function. That's nice. So how about tail? Right, okay, so tail of a unit list and tail of a list that starts with 2 elements is quite easy, which is return the empty list or remove the first element. But a tail that starts with 1 element, we have to remove this element, and now we only have q and u left. And there are some interesting cases to consider there. So we use a helper function that's called more0 q and u. So more0, if the recursive sequence is empty, there's some 2 cases to consider. So we have to redistribute the elements on the right-hand side over the sequence. But if the recursive sequence is not empty, then we can look at the head of that sequence. And there will be 2 elements there. We can take those 2 elements and start our sequence with those. And then we remove those 2 elements recursively from the recursive sequence. So we can see that tail is a recursive function. It calls more0 that could even call tail. And the number of recursive steps that we can do is the same as the depth of the sequence, which is again logarithmic. So this is a logarithmic function. So for this implementation that we have here, we have head, cons, and tail with the right worst case complexities. And by symmetry, we have last knock and init, so that's good. But how about plus plus? Can we implement plus plus on this data type in a satisfactory way? Well, let's look at an example. We have a sequence that ends with an A and a B, and another sequence that starts with 1C. And we're going to append those 2 sequences. So what should the result be? Well, we start with U and we end with V, just like these sequences did. But the recursive sequence in the middle should be P, and then an A and a B, and then a C, and then Q. But P is a sequence of pairs, and Q is also a sequence of pairs. And somehow we need to insert 3 elements in between these 2. We don't want to deconstruct either P or Q in order to have space with these. So we have to add 3 elements in between 2 sequences that both have pairs. That's not possible to do in a nice way. And so if you can implement this on this data type, but it will not have the nice complexity, logarithmic. So we have to solve this somehow. And this example makes it sort of easy what we can do. Instead of requiring that there's pairs of things in P and Q, we can also allow pairs, either pairs or triples to occur in P and Q. So that's what we're going to do. So let's try number 4. So our sequence data type looks like this, and the change we have is that it's not pairs here anymore. Now it says tuple of A, and a tuple of A can either be a pair or a triple. So we have to add some cases here and there to our functions. So let's see what those changes will look like. Well, if you look at head and cons, the changes are either no changes or very trivial. So I'm not going to show you the implementation of head and cons. The implementation of tail is actually the same as before, but the implementation of more0 slightly changes. So previously we said case head q of a pair x and y and this, but now it can also be a triple. So what should we do when the recursive sequence starts with a triple? So here's an example. If we take the tail of a sequence that starts with 1A and then has a recursive sequence that has a triple B, C, D, what should the result be? Well, we want to throw away this A. And what should the resulting sequence start with? Well, it can start with 1 element or with 2 elements. But if it starts with 2 elements, there's only 1 element left here. That's not a good idea. So the only thing we can do is to take 1 element from this triple. That's the new start of our sequence. And turn this triple into a pair where we just remove this element from there. That's the only thing we can do with our data type. So let's implement that. So go back to our case here. This was the previous case. But if the head of the recursive sequence is a triple, we take the x, we make a sequence that starts with that x, and then we chop away the first element of the first triple that occurs in Q. So I'm going to use 2 helper functions. Chop, which is defined here. Chop takes a triple and turns it into a pair by removing the first element. And map1, which takes a function and only applies it to the first element of a sequence and not to none of the other ones. And that becomes a logarithmic function because the only recursion happens here, and q is a sequence that is twice as fast as the original one. For completeness, we have the definition of map1, so its complexity is constant. So the current implementation works for head, cons, and tail. Let's look at what it does for ++. Well, before we can look at ++, we are going to define two helper functions that are going to be useful for us. The first function converts an element in the sum data type into a list, and that function is called toList. It takes a sum A to a list of A, and I've annotated the list that I'm using here with the possible lengths it can have. The other helper function takes a list and turns it into a list of tuples by combining the elements in the list that are next to each other. That function is called toTuples. It takes a list of A and it returns a list of tuples of A, and it's a recursive function. So empty list is empty list. It has two special cases for 2 and 4 elements, and all other cases turn into triples recursively. And I'm going to use it on lists of length 2 to 6, and it will turn that into 1 to 2 tuples. So let's look at the implementation of ++. Well, ++ is going to be defined in terms of a helper function that I call glue, and that's going to do the actual work. And glue takes 3 arguments: a sequence, a small list of elements that has to be inserted between these 2 sequences, and another sequence. You can see it's natural to introduce this function because of the ending and beginnings of sequences that have to be combined and be inserted between sequences. So what does glue look like? Well, here's the type of glue. It takes a sequence, it takes a small list between 0 to 2 and 2 elements, and another sequence, and glues all of these together. And glue is quite complicated, so let's look at it in steps. There's 5 cases to consider, 4 base cases and 1 recursive case. The base cases are when one of the lists is empty or has 1 element. And in that case, there's only 1 sequence to consider. And so we just add elements to that sequence using cons or snoc, depending on where they should be added. The interesting case to consider is when both sequences are more sequences and we have some elements in between. So the result is, of course, going to be in more sequence as well. And the start is going to be U, the end is going to be R, and it's going to be the sequence P glued with the sequence Q, and the elements that are going to be in between are elements from V, X's, and W. This is what that looks like. We get a more starting with U, ending with R. We recursively glue P and Q together, and the elements that we have between is the following. V is a sum data type, and W also. We turn those into lists. We append those lists together using the list append, which is what this operator does, the normal Haskell list append. So we get a list of elements, and finally we turn these into tuples because P and Q are sequences of tuples, not sequences of elements. Okay, so this is a recursive function. We recurse over P and Q, which are recursive subsequences that are twice as fast. So we can see that the complexity of glue is logarithmic, as long as we obey these list sizes. Okay, so that leads us to this table of complexities. We have all the worst case complexities of head, tail, cons, last, init, and snoc, and ++. How about the amortized complexities? We would like to have constant time amortized complexity for all the simple list operations at the back and the front. Well, they are not constant right now. So if we look at tail, there's one interesting case where tail does recursion, is when the sequence starts with a 1. In all the other cases, it doesn't do recursion. So only when the sequence starts with the 1, it's logarithmic time. And cons, only when the sequence starts with a 2, it does recursion. But no other cases doesn't do recursion. So only when it starts with a 2, it's logarithmic. The bad thing happens when, because tail transforms sequences that start with the 1 in sequences that start with the 2. And cons transform sequences that start with the 2 into sequences that start with the 1. So these two functions in sequence enable each other's worst cases. And so you can construct a worst case that where every occurrence of tail and cons will take logarithmic time. So we don't want that. So since we only have 2 cases, 1 or 2, And either case, one of these cases is, all of these cases expenses for one of these operators. We can never hope to be cheap in any case. So how do we fix this? Well, if we add one more case that is cheap for both of these operators, then we have a chance of getting a constant time amortized complexity. So how do we add one more case? Well, we just add 3 elements. So the sum data type now can have 3 elements. And if the one case is still expensive for tail, of course, because 2 and 3 are easily converted into 1 and 2 when you take the tail. And for cons, it's the 3 case that's become expensive because 1 and 2 are easily converted into 2 and 3, just adding one more element. But the 3 case that is expensive. If we now make sure that this expensive case for tail turns into the cheap case for both, and the expensive tail for cons turns into the cheap case for both, then we have a chance of getting constant time amortized complexity. Let's see. So we add one more constructor to the sum data type, and let's see what happens to the implementations. So cons, it gets one more case, interesting case at the end. It gets a sequence that starts with the 3, and we have 4 elements, the one we want to add plus the 3 that we already have, and we divide them up into a sequence that starts with those 2 and recursively adds those 2. So again, this is the recursive case. It's the expensive case. It starts with a 3, but it turns into a sequence that starts with 2. So that's good because 2 is cheap for both. Let's look at tail. Here's a new implementation for tail. Here are 2 extra cases we have to add, but they aren't very interesting. There's not much choice you can do. Okay, so what happens when we add 3 for the append? Well, the only function we have to change is the toList function. We have to add one more case to it, and we can get a list of 3 elements, and that's reflected in the type. And the 2 tuples and the glue functions don't change their implementation at all. The only thing that changes is the annotations of the lists that are involved, because they can be a little bit bigger now. But they're still bounded in size, so nothing changes there. Okay, so this is the final data type that, as you saw before, and incidentally, it's simpler than Hinze's and Paterson's data type because they had an extra constructor 4 in their implementation. And these are all the complexities that we all satisfy. So to sum up, we explained finger trees, and we managed to even simplify finger trees. We use types, very detailed types. Sum and tuple were never merged into one type, as some people suggest when they see this. And that helped catching lots of errors. Also, quick check properties helped catching lots of errors, both in the functionality as well as in the amortized complexity. So those were good things to use. As future work, we want to simplify the use of 2 lists and 2 tuples. It feels very unsatisfactory to convert to normal Haskell lists in the middle of a data structure. The natural question is, are the simplified finger trees more efficient than the original one? We have not checked this because it's hard to compare a very optimized data structure against a data structure appearing in a functional Perl. Although I don't believe it's going to be more efficient. We just simplified the number of cases, but not the actual implementation. We would like to look at the nice implementation of indexing. We haven't done that yet. And the amortized complexity analysis I showed you is for sequential amortized complexity, not for persistent amortized complexity. And I would like to that to be simpler. Okay, that's all.